Right, we're just going to look at linear equations, graphical solution. Dead straightforward this. Consider the following experiment. Imagine a spring. You've got a spring and you're just holding weights on and it extends. Then you put a heavier weight on, it extends more. You put a heavier weight on, it extends more. So when no weights are on, 0, I'll use this. There's no extension, of course, in millimetres, that's fine. We'll put a weight of 1 Newton on. So you clicked a Newton on, it's extended a little bit, and it's extended by 8.5 millimetres. 2 Newtons, and it extends by 16 millimetres. 3 Newtons, 4 Newtons, 5 Newtons, up to 6 Newtons, and it's extended 50 millimetres. Now, we could plot this as a graph, and you'll notice that at no Newtons, there's no millimetres. At 1 Newton, it's 8.5 millimetres. At 2 Newtons, it's just over 15, 16. At 3 Newtons, so these numbers here have been plotted into a graph. You can see it wavers a little bit, and what you do really in reality, when you're doing experiments and natural things, it never quite works out exactly like a straight line, but it's really close. And you'll do a line of best fit through it. So you'd have to get your ruler, ideally a clear ruler, or use a computer, and construct a line of best fit straight through it. That line of best fit can be interrogated to create a formula that will let us predict future results. So for instance, we only got up to 6. What if you wanted to know how much the extension is at 7, or 8, or 9, or 10, or 11, and so on? So you only have to do a little bit of work, and then that formula will let you predict lots of other results. That's why this is used. So just looking at this slide, let's have a genuine problem then. We know it up to 6. Let's say we want to know the extension in millimetres if 11 newtons is the applied weight, the applied force. Fair enough. What we'll do first, we have to find the gradient of the line. We have to find how sloping it is. And depending on how sloping it is, that will tell us how many millimetres we're going to be looking at. So obviously if it's not sloping much, there's not going to be many millimetres for every time you put a weight on. If it's sloping a lot, there's going to be a lot of millimetres extension for every time you put a weight on. So first thing we need to get is just how sloping is that line. And of course that's called the gradient. Now to work it out, draw a triangle anywhere on your straight line. I've gone from like known points, which makes sense. Now 1 and 4, I know where they are, and I also know what the reading is in millimetres at 1 and at 4. So what we'll do is, I'll just label the triangle up for you so, so you know what I'm talking about. So I've got triangle A, B, C, and we want to work out the distance up between A and B, so I'll have to take that number from that number, and then the distance across between A and C, which is quite easy because it's 4, take away 1, so that one's going to be 3, and the other one, looking at the results before, the value at B when 4 newtons is applied, the extension was 33, and at 1 the extension was 8.5. So this distance here is going to be 33 take away 8.5, so I've got AB, which is 33 take away 8.5, divided by A to C, which is 4 take away 1. So 33 take away 8.5 is 24.5, and of course 4 take away 1 is 3. When we divide that together, we get an answer of 8.2. Right? That's just a regular number. We're going to use that shortly. There's no units to that. It's not 8.2 millimetres, it's just 8.2. And the reason I've shown it with a plus sign in front is because a positive gradient goes that way, and a negative gradient goes that way. So if this said minus 8.2, if the line was going that way, we'd show it this way with a negative sign. I've just captured that here with this sentence. As the line slopes in this direction, it's positive. And then if the line slopes in the opposite direction, of course, it's negative. We need to work out next, we've got the gradient, we know it's 8.2, we need to work out where that line cuts through this axis. Now we can see conveniently that it cuts through at 0. However, it could cut through at 15. It could cut through below there, and you'd have to extend that down, and then you'd extend your line, and it might cut at -10, -15, -6, whatever. You've just got to know where that line, your line of best fit, cuts your y-axis. So if you haven't drawn your line long enough, you're going to have to extend it so that it goes through that axis. This is where it cuts the y-axis, called a y-intercept. In our case, we've already identified our intercept is 0, right? So we know that it's going to be 0 for the number there. So we've worked out the gradient and the y-intercept. The next bit's pretty easy. All straight lines follow this format. Your gradient times by the number you want to know. In our case, remember, we're not doing this for fun. We're going to work something out. We want to work out the amount of extension at 11 newtons. So a lot of people get bogged down and start thinking about all this and forget that there's an actual question to be answered. So 11 newtons will be our value for x. It's saying, what would you like to know the answer for? What are the conditions? So it could be 11, 12, 20, whatever. In our case, it's 11. So the gradient, we know, is 8.2. X-axis value, the value on this axis, well, we want to do it for 11. And then plus the intercept, and we've just worked out that the intercept is 0 from reading the graph. Now, of course, mathematicians like to use algebra to represent this. For gradient, they use the letter m, and for the intercept, they use the letter little c. Now just bear with this. If you're more comfortable using plain English, then fine, but you will see this formula everywhere. The gradient we know times the x-axis value that we want to know at the intercept is usually written as y equals, and then m for gradient, x for the number you want to know, and plus c for adding on what the number is where it cuts the y-axis. In our case, let's fill those numbers in. So if x is 11, because 11 newtons, then y equals, this is your y-axis, so the extension, whatever axis is there, it might not be extension in millimetres, this works for any straight line graph. So the extension, y equals 8.2, which is your gradient, times by 11, because that's the number we want to know, the x value, 11 newtons, plus 0, because the line cut the y-axis at 0. So when we put that into a calculator, we get 8.2 times 11, add nothing. That gives us 90.2. 8.2 times 11 is 90.2. Add 0, of course, remains 90.2. So when 11 newtons is added to that spring, it will extend, it will stretch by approximately 90.2 millimetres. If you wanted to know it for 12 newtons, it will be 8.2 times 12, add 0, and it will be obviously more than 90. That's it for straight line graphs, that works for everything. The only thing you have to do is calculate the gradient properly and get the y-intercept properly. And if your line doesn't reach the y-axis, extend it, right, your line of best fit. There you go.